but this will give you kind of more so some kind of insight into how we would build this using code. So this is directly taken from the IBM Qiskit textbook, section 1.2. It's really really helpful as just an educational resource, and you can find like a more in-depth explanation to this stuff in there.
Teddy, do you mind if I say something?
Yeah, go for it. Go ahead.
Me and Teddy have talked, and I think that we're gonna. I think we agreed, Teddy. We're gonna start doing, instead of the 45-minute presentations with a 15-minute break, we were gonna shorten it, do kind of 30 minutes a piece, and then just kind of flow it. So now it's 5 to 6, a little bit less of a time commitment. If anyone out, if somebody is busy from 6 to 7, hopefully this could, or you know, you got a lot of homework, you only have an hour to spare. Hopefully that'll convince, you know, make it a little bit easier on everybody. So yeah, that's what we talked about.
Oh yeah. So I'm gonna first dive into just a review of last week. And so we went over a few things, the first of which was the encoding of information. And specifically in this application, like more generally, we can think of the fact that we do lots of things with our computers. We stream videos, and we do math, and we play games, and browse the web, right? And there's tons of information that is being interpreted by us visually in some way or another, whether it's language or just a visual depiction of something, whatever it is. It's very easy for us to understand. It's intuitive, but like the same can't be said for the same information with respect to a computer. A computer working with electrical pulses and signals has a really hard time interpreting things like pictures and words. Instead, what it can interpret is the strength of the signal, and it can kind of categorize that into being like a 1 if the signal is on or above some threshold, or a 0 if it's below that threshold. And so when we do computation, when we stream videos, when we browse the web, ultimately it has to be translated into 1s and 0s. And depending on the data, the scheme is unique. But what we talked about in our simple case of adding together two numbers is encoding those numbers and bringing our numbers that we usually think about in base 10 down to base 2. And so if you are unfamiliar with the way that base 2 works, there's a lot of great resources that that will be more helpful than I. But in a nutshell, we count to, like, on our fingers, say from 1 to 10, and then we start over at 11, right? And do the same thing, 1 to 9 to the 0, start over. And so that like 1 to 10 is our base. If we were to count in base 2, we would just have two numbers to work with, 0 and 1. And so stringing together these 0s and 1s and kind of like carrying over to the left the higher value of like the previous bits will allow us to encode large values into bits. And so what I mean by this more specifically is that for each value in a binary number, for each place, it's representative of 2 to the power of that place. And whether there's a 0 or 1 there is indicative of the fact that there exists within this greater number 2 to that power. And so if we think about the number like 4, well, 4 will be represented by 1 0. And the reason for that is because 2 to the power of 1, it's 1 0, right? And so the first place is representative of 2 to the power of 1. And in the number 4, we don't have 2 to the power of 1, which is 2, right? And like you might say that, well, we do, but you want to fill up the left side before you fill up the right side. And so if we like start from the left, we could say that, okay, at the second place, at the left place of this like 2-digit number, that's representative of 2 to the 2, which is 4. And we do have one of those. That is the only number that we have in 4, right? So to represent 4, we would have 1 and 0. And that's like might not be super clear, but like I said, lots of resources online that go over base 2. And when we add numbers, in the simple example of just adding 2 bits, it's really the case that we can break this down into 4 different scenarios. The first scenario is that we're just adding 0 and 0. And in that case, we're just going to get 0, right? Nothing surprising about that. Or we can add 0 and 1. And this will result in 1 or 0, 1, right? And if we add 1 and 0, we're also going to get 1. Nothing should change there just because we move the terms, right? Addition is commutative. And so if we finally add 1 and 1, this is the case that it gets weird. Like in base 10, we would say that's 2, but well, in base 2, we don't have the number 2 available to us. We have to start over, right? And so what we do is actually put over this 1, 0 right here to represent the value of 2. We carry the same way that we would do in base 10 addition, we carry over the 1 to the next place. And I messed up previously when I said that example of 4 being 2 to the 2. So the rightmost bit is 2 to the 0, which is just 1. And then it goes 2 to the 2, which would be 2, and then 2 to the 1, which would be 2, and 2 to the 2, which would be 4. So 4 would be represented by a 1, and then a 0, and then a 0. That's like, but irrelevant for this. What we care about is that when we're adding 2 numbers, we can break them up into 4 different cases. And these are those cases. And once we actually orchestrate this circuit, it's going to look something like this. And we don't have to go into what this means just right now, but we will in the next slides, I believe. Actually, let me do that right now, just to review what we talked about last week. So the gates that we're going to use is the invert bit, which is just a not, the conditional not or C not, which is a not if the target bit, if the control bit is a 1. So it's depicted here. We've got like, it's a 2-qubit operation. And what we're doing is we're saying, okay, let's look at the control bit. And if this control bit is 1, then let's just apply a not somewhere else. Let's apply a not to another qubit. But if the control bit is 0, then we're not gonna apply anything. We're gonna leave that second qubit as it is, and just allow the continuation of the circuit flow. And then we have a Toffoli, which it can be like denotated by CCX or controlled not. And the reason for that is because it's the same idea of a controlled not, where you kind of have this control, conditional not, where you have this control and it dictates whether you're applying a not on another qubit, but it extends that to having 2 controls. And so this allows us to build this half adder that we want, right? And really capitalize and emulate these cases that are going on right here. So to kind of break down the cases and like what they can lead to, or what patterns we need to identify, we can first break it down as like the individual bits, the left bit and the right bit, and determining the values of that left and right bit. And so if we look at this, the only time that we will have the right bit being 1 is when the qubits are different, right? In this case and this case. And so down here, like this is the right or the left qubit that's being affected. And up here, there is like no operation at all because it's 0, 0, right? But when they are different, that's going to result in us actually changing the right qubit, right? And so what we're going to do is we're going to, with that information, apply these 2 conditional not gates. And what we see here at the beginning is the like not gates being put onto our inputs. And these 2 inputs, this Q0 and Q1, are the numbers we want to add. But if we remember from last week and the previous weeks, when you initialize qubits, they initialize to 0. So if we were to just start adding, like if we were to just make some circuit that adds, we would continue to just add 0 all the time. Like it would just never work because they're initialized as empty or as 0. The same way that if you initialize a variable in most languages, they'll just in classical languages, they'll initialize to null or 0 or none. And so we first initialize or encode our information back here. And now have it after this barrier, which is what this is, really just giving our mind a break and saying, okay, we're done with this step, we're on to the next one. We have now encoded our information. We have now created these qubits that we want to add together. And so what we're going to do is we're going to apply a conditional not to qubit 2. And qubit 2 and qubit 3 are what we call ancillary qubits. They're not necessarily like something that is used directly as input, but they are used to construct the output. So even though we took in two bits to add, we created 4 qubits because we need that extra space. We can't just write over our qubits. We need this extra space to be able to like break this information down and move it, or rather not break it down, but move it around without disrupting our state. And so applying this not on this second qubit allows us to say if the qubit 0 is a value of 1, then let's flip qubit 2 from 0 to 1. And if qubit 1, if that second qubit is also a 1, then let's flip this qubit again from 1 to 0. And so this is going to address the left qubit. The reason for this is because if they're the same, so I messed up. It's not actually these that we're addressing. It's this case right here, where yes, like when they're different, we will address that with the conditional, the Toffoli. But what this first segment is doing is saying, okay, when we have these 2 qubits being the same, then we want to change this first value, the first qubit to 1 and the second one to 0, or the right one to 0. And so that takes care of the left qubit, and then the right qubit is taken care of by the Toffoli, which allows us to just say, if these are both 1, then you change this third qubit from 0 to 1. And that should handle our 4 cases. So the C naughts take care of our left bit, while Toffoli just takes care of our right bit. But something that was highlighted in the video is it's not as simple as just like running this and getting an output, because if we ran it once, they're still very much probabilistic, and we're not going to get a like sound answer unless we run it a sufficient amount of times and then extrapolate the probabilities for each qubits. Now we'll move on to like pass the theory into the actual building, like what this lab is about. These are kind of the steps that you will take when building a quantum computing circuit or building a procedure. The first one is Encode. And what you want to do here is actually get your classical information into something that can be interpreted by a quantum computer. Lots of times, like we want to apply quantum computers to aspects or field applications problems that aren't quantum. And so this may be within finance, it may be within just like engineering or like classical mechanics, whatever it is. We're not always going to have quantum information. That's the case in physics a lot, but like and chemistry, but for a lot of the business applications that make quantum computing so attractive, the information is classical, and it can offer us a speed up if we can get this classical information into a quantum interpreted state, right? And so there's a few ways to do this. You could either do amplitude or you could do state encoding. And when we do amplitude encoding, the information that we have, we're putting it into our probabilities. And our probabilities are representative of the information that we're computing, right? So if we wanted to add 2 numbers, well, adding those 2 numbers through like encoding them in amplitudes would consist of us like adding the amplitudes together, not adding the states like we're doing here, right? In this example, we're doing state encoding because it's such a simple thing, because it's just ones and zeros. We can just have our qubits be directly representative of the information. And so the amplitude's right there at 100% at 0 initially, and then we use a not to actually change the qubits themselves as states, but not their probabilities. If we were putting Hadamard gates and throwing things into superposition, then we'd be playing with the probabilities. But it's still very much the case that when we apply this not right here, there's a 0% probability of qubits 0 and 1 being 0 right here. And then we do the not, and if you not a 0 with 100% probability of being 0, it's going to be a 1 with 100% probability of being 1. So we're not doing anything but state encoding here, which is a lot simpler and easier. The next step is the computation step, which is simply just applying whatever computation you wanted to onto this superpositioned or quantum represented state or set of states. And the output is likely a quantum state, so you can't just call it a day here. There's still lots of work to be done on changing this into something that's easily interpreted by us and is in a classical manner. The last step takes care of that. The last step is all about if we have superposition in our state, we would like to apply some kind of interference to make it possible for us to measure what we want to measure. If for example, in Shor's algorithm, when we're computing the like possible prime factors for a given number, we want to kind of try all the possible prime numbers or all the possible numbers and compute over all of them, find the solution for all of them, and then only take out the right answer, right? And in that case, we need to apply some kind of interference to make sure we take out the right answer. Otherwise, we might just be getting garbage. And in our case, in the half adder, we don't need to do any kind of interference at all because we don't do any superposition in this circuit, and therefore, like, don't need to actually mess around with making sure that we get the right observation. Those probabilities are still at 100%. So for the initialization, this is what's going on. The first thing is just importing the Qiskit modules we need, right? And so from Qiskit, we want to import quantum circuit, which is a library or a module that allows us to create circuits and edit them and build quantum circuits. And when we think of a quantum circuit, this is like your program, because it's kind of like you're using Python to make a quantum program. You're using Qiskit within Python, and specifically the quantum circuit module, so that you can make this quantum program then that you can then deploy using assemble and air. And assemble is the module that's responsible for turning this kind of like this. If you can think of like a compiler and the way that compilers work, you first have like this program that a programmer wrote, and then you actually have to get it into a form that's able to be interpreted by the machine, and so you compile it. And assemble is very similar to compilation. It takes care of moving our circuit from the drawing board into a like ready to deploy object that can be used by air. Because air is the simulating module. It's responsible for making sure that we can actually deploy our quantum circuits and get results, whether it's locally on a simulated quantum computer or on IBM's actual quantum computers. The next thing that we're going to be importing is primarily just responsible for visualization. It is very similar to matplotlib if you've worked with that, and not super important in terms of not super technical like the other modules are, but it is like very, very helpful to visualize the results of your shots or your simulation, right? And the last thing that we do is we actually initialize our simulator. So we say sim is equal to air.get backend quantum assembly simulator. And so what this is doing is saying, okay, when we run our quantum circuit, we need to actually have somewhere to run it. And sim is that somewhere to run it. We use the air module and we say, okay, set the back end, set what we want to run it on. And what we want to run it on is this quantum assembly language simulator, which is just deployable from our machines. The first step, that encode step, where we actually encode our information. We say quantum circuit is equal to quantum circuit for 2. And what those parameters represent is the number of inputs or qubits and the number of outputs. And so we have 4 qubits, right? Back here, 0 to 3, and we want to measure 2 things because we don't need to have anything larger than a 2-digit number or 2 binary digit number if we're just adding single binary digit numbers. Next, we will just encode the information. And so this is really just applying this .x or .not. The .x is simply representative of the application of a NOT gate. You say quantum circuit dot add a NOT gate to qubit 0. And then the same thing, add a NOT gate to qubit 1. And so what we're doing is we're saying these qubits that were previously just initialized to 0, let's encode them. And let's say they're both equal to 1. And so now the compute part, the first thing that we're doing is creating a barrier. And that quantum circuit dot barrier is just adding this right here. We then go on to say, let's take care of the left bit. And so with that, we're saying quantum circuit dot add a conditional NOT with a control of 0 and a target of 2. Then we say quantum circuit dot conditional NOT with a control of 1 and a target of 2, again, right, to take care of that, which is really just the application of an exclusive OR, because if you think about like the cases that we need to apply or that we need to consider with this, we want this value to mean something or to be a 1 whenever one but not both of them are 1, right? So an exclusive OR is just saying when there's 0 and 0, they are, neither of them are a 1, right? And so like we don't have OR. Like if we break down like an exclusive OR just to like a simple OR, a logical OR, what that's representative of, like we want 1 or both, right? An exclusive OR is we want 1 but not both. And so with an OR gate, this would evaluate to 1, this would evaluate to 1, this would evaluate to 1, right? And this would evaluate to 0. With an exclusive OR, these 2 would evaluate to 1, and these 2 would evaluate to 0. And so, like I said, this is wrong. This is actually the right bit. And so in order to get that right bit, we apply an exclusive OR. And an exclusive OR with our quantum gates is just a controlled gate, a controlled NOT, with the control being the first input and the output being this ancillary input, or the target being this ancillary input. And then the same thing applied to the control as the second input, right? And so these again messed up. This is right and this is left. Hopefully y'all see that. I'm sorry for messing that up and making that a bit confusing earlier. But again, that's just addressing this case right here. The fact that like we care about changing this right bit, this right place, whenever these are the result of this is an exclusive or an exclusive OR is applied to these inputs, right? And so with that CCX or CX and CX, we get this down here. We get these 2 gates. These 2 gates are the controlled, the conditional NOTs. Then we move on to actually taking care of the left bit, right? And that's just addressed using a CCX or a Toffoli, which, like I said, is just like the conditional NOT, except instead of 1 condition, we have 2 conditions or 2 controls, right? And so we say we want to take our controls being 0 and 1, and if both of them are 1, then the third qubit we want to apply a not. And so what that's allowing us to do is look at this and think, okay, we've got these qubits, right? We've got these like zeros that were initialized to 1. And then this place that we're going to put the output, well, it's by default initialized to 0. So if it's the case that both of these are 1, then right here, we are going to check that they're both 1. We're going to say, okay, they're both 1s. And we're going to say, okay, let's apply a not to this third qubit, or qubit 3, the fourth qubit. And that's changing that 0 to 1. And that's addressing that step right there. So like I said, when we have 1 and 1, it applies this not down here. And that not down here is representative of this left bit. And allows us to take care of the carry part of our addition, right? The final thing is extract. And so the first thing we do, we make a barrier, just like we did before. And then we extract the left and right qubits. So we say quantum circuit dot measure, we measure the second qubit onto the 0th output. So that's doing this right here. It's saying the second qubit, qubit 2, onto the 0th output, right? And the same thing, qubit 3 onto the first output, right here, right? And now we start to use this, the assemble module and the simulation to actually execute our circuit, right? Because up until right here, this was kind of like still our drawing board. This was still our program that we were writing, and it's in human readable language, and a computer can't interpret it, right? What needs to be done is it needs to be compiled into this object that is similar to like a binary that we can actually run. And so that is our deployable circuit. And we simply say assemble QC output. This should not say QC output. This should say quantum underscore circuit. And the method is simply taking in that circuit and changing it into, it's compiling it into something that can actually be deployed. And so then we say result is equal to sim, that simulator, which is our quantum assembly backend, sim.run this circuit, and then we store the result. We say dot result to get the actual results from that. And what that's doing is it's getting us not just this one run, but it's getting us multiple runs, and enough for us to actually make some sort of statistical inference into the probabilities for each state, right? And then we say counts is equal to result dot get counts, just a method that allows us to extract the actual like number of times that each state appeared as the output. And finally, we plot the histogram. And the result is when the inputs are 1, 1, and this circuit is formed, an output with a probability of 1.0 of 1, 0, which is the result of the addition of 1 and 1. So 1 plus 1 is 2, and in binary, that's 1, 0. Something to note here, though, is that this was on the simulator. And so if we were to run this on IBM quantum machines, we would not get this result. We would likely get something where we get like maybe 75 or 60% 1, 0, and then the rest of the time, just a bunch of random junk. And that kind of like is something that's, it calls back to our talk last week or the week before about the NISQ era, and how we're not quite at something that could be like a reliable source of computation. This is the ideal scenario. This is what this half adder could have run if it was deployed on a fault tolerant quantum machine, but that's not the case if you were to deploy it right now. So these slides are online at the GitHub. I encourage you to take this code and run it yourself, play with it, and mess with the different inputs just by changing these two lines right here. You can remove line 9 and you'll end up with adding 1 and 0, or you could remove both of them and you add 0 and 0.
Yeah, and Is it okay if I talk real quick, Teddy?
Yeah, absolutely.
I was just gonna say, yeah, the IBM website also, if you don't like working with Python, the IBM has a more user-friendly interface for dealing with quantum gates. It looks like that graphic right there, where you apply the boxes on the lines, which is pretty interesting. And yeah, fun thing that I was looking into is like the interference of, since quantum computers are so delicate, and even just like any stray electromagnetic radiation can completely screw up the computation. Like the more qubits that you have, the more you need to run these programs over and over and over again to get a good statistically significant answer. Because if you only run it 10 times and you have a lot of interference, then it's really gonna it's kind of pointless. And it's interesting how regular computers are kind of the same way. We've just gotten so good at making them that they hardly ever have any type of interference now. But occasionally a random bit in a computer will flip due to like a positron or something like that. Some just random subatomic interference, which can then screw up an entire computer. And it's just a lot more likely with quantum computers because they're so delicate because of the superposition stuff. Yeah. That's all I had.
Thanks, Will. That is also all I had. So if there's any questions, I'd be happy to address them.
All
I
good.
have no questions, but
Oh, my
thank
bad.
you for the talk.
Absolutely. Oh,
Yeah,
yeah.
of
Yeah,
course.
thank you so much.
Thanks for coming, y'all.
Yeah,
I
yeah,
hope y'all have a great week.
Yeah, I hope
You
you have a
too.
great
You
week.
too.
And we're right at 6. That's perfect.
Awesome. I'll talk to y'all later, y'all.
All right. See you guys later.